Hello, welcome back. In this video we'll discuss the nanoscale. Nano is a prefix that is derived from Greek. The prefix means dwarf or small or very small. Mathematically speaking, nano means a billionth part, or it is 10 power minus 9. In physics, when we say nano, it means a billionth part of a unit. For example, when we say 1 nanometer, we mean to say that it is 10 power minus 9 meters, or it is 10 power minus 3 micrometers. As you know, 1 micrometer is equal to 10 power minus 6 meters, or the same thing is equal to 10 angstroms, as an angstrom unit is equal to 10 power minus 10 meters. So 10 angstroms, they make 1 nanometer, 10 power minus 3 micrometers, they make 1 nanometer, and 10 power minus 9 meters, they make again a nanometer. To get a feel of the numbers, let us try to look at a couple of examples. For instance, the human hair thickness will be about 80,000 nanometers. Similarly, the RBC length, that is the red blood corpuscles length, will be about 7,000 nanometers. At 0.1 nanometers, that is angstrom units, we have the atomic scale, and the nano world is a borderland between the quantum world and the macro world. The nano world is a borderland for quantum world and macro world. The quantum world generally corresponds to the 10.1 nanometers or so. The nano world generally will be in 0.2 to 100 nanometers or even slightly more. Anything that is greater than 10 power 4 nanometers is generally referred to as macro world. We shall see some examples. Here we are representing 10 power minus 10 meters on the extreme left side and 10 power minus 2 meters on the right side. The left side corresponds to 1 angstroms and the right side corresponds to a centimeter. We use the centimeters to represent the diameter of a tennis ball. Similarly, an ant will be about 5 millimeters, so we express the length of the ant in millimeters. A human hair will be about 10 power minus 4 meters, so we use roughly 100 micrometers. We use the micrometers to express the length of a bacterium. Similarly, the viruses, which will be in 100 nanometers. So here we use the nanometers and the length is about 10 power minus 7 meters. DNA molecules length will be about 10 nanometers. Similarly, the bond length of the molecules will be in a nanometer, and less than that will be the atomic radii. So we use angstroms. We shall now see some examples of size from molecular to macro. In this table, we have 3 columns. The size in nanometer in the first column, we have the examples given in the second column, we have the terminology used to represent the examples in the third column. 0.1 nanometers to 0.5 nanometers lengths, they correspond to individual chemical bonds, so we call them as molecular or atomic distances. 0.5 to 1 nanometer is the small molecules, for example hydrogen, and these are considered as separations or the molecular distances. 1 nanometer to 1000 nanometers generally will have the protein, DNA and inorganic nanoparticles. So this scale is generally referred to as nano. In the 10 power 3 to 10 power 4 range, we'll have the transistors on a silicon chip, the size of the living cells, and the human hair. They are the examples of this range, and we call them as microscopic. And please recollect that we have a branch of electronics that is called as microelectronics. So generally that refers to 10 power minus 6. Any object's parameter that is greater than 10 power 4 is referred to as normal bulk matter. We call them as macroscopic objects or macroscopic systems. We shall now see the significance of the nanoscale. When we take a material in its nano form, then we observe a large deviation of the physical properties of the material when the material is taken in its bulk form or the macroscopic form. Many of the properties of solids, they depend on the size of the solid. Microscopic details become averaged out in bulk materials. So what happens generally is the microscopic details become averaged out in bulk materials. In case of bulk materials, the properties such as density, elastic modulus, resistivity, dielectric constant, etc. are averaged properties, microscopic properties of the material measured in various directions under different conditions. Many properties of materials they change in the micrometer and nanometer range. Properties of materials change in micrometer, nanometer range. As the material becomes smaller and smaller, we notice that the averaging effect will no longer is applicable. There we start observing the behavior of the material in its nanoform. Now we shall see the reasons why certain properties are exhibited by the nanoscale materials. The first one is the nanomaterials have a relatively large surface area when compared to the same mass of material produced in a larger form. The nanomaterials have a relatively larger surface area when compared to same mass of material produced in a larger form. Since the nanomaterials have a relatively larger surface area, these materials when compared to the bulk materials, they will have different physical properties. For instance, if you take 1 gram gold in its bulk form, let us say we'll take a small piece of gold whose mass is about a gram, and we shall also take 1 gram gold nanoparticles. And if you try to measure the physical properties of these two substances, that is, the gold in its bulk form of a small piece and gold in its nanoparticle form, then we notice that the physical properties of these two are not the same. Meaning, the gold in its bulk form will have a different set of physical properties, and the very same gold in its nanoparticle form will have altogether a different set of physical properties. The reason is mainly due to the relatively larger surface area of the material in its nanoparticle form when compared to the larger form of the material. The second reason is quantum effects can begin to dominate the behavior of matter at the nanoscale, affecting the optical, electrical, and magnetic behavior of materials. When the size of the material particles they become smaller, if they can be found on the nanoscale, then the quantum effects they start dominating. As a result, also we can expect different physical properties. Quantum effects can begin to dominate the behavior of matter at the nanoscale, affecting the optical, electrical, and magnetic properties. Molecular. Please recall that the main source of magnetism is spin of electrons. The moment you say spin of electrons, we are referring to the quantum mechanical property of an electron, because spin itself is a quantum mechanical concept. Spin is quantum mechanical property of electrons. When the material becomes smaller and smaller, the quantum mechanical effects can begin to dominate the behavior of matter at the nanoscale. Thirdly, the physical properties are generally characterized by certain critical length. We know that the physical properties of materials are generally characterized by critical lengths. For example, the electrical conductivity of a metal is determined by mean free path. While discussing the electrical conductivity, we have seen that the electrical conductivity depends on the mean free path. And what is mean free path? It is the distance that the electron travels between two successive collisions with the vibrating atoms. It is the distance between two collisions or two successive collisions. Generally, the mean free path will be in micrometers. Here we have a situation where the length of the particle or the dimensions of the particle will be in nanometers, and this is less than micrometers. Or one of the dimensions of the material is smaller than the critical length. The nanomaterial exhibit properties that are different from the corresponding bulk materials. Because of this fact, the nanomaterials, they exhibit properties that are different from that of the bulk materials. And lastly, the bulk properties of materials often change dramatically with nano ingredients. Please try to recall that the way we have produced the extrinsic semiconductors. We have initially taken an intrinsic semiconducting material, and to the intrinsic semiconducting material we have added certain dopants. They could be pentavalent or trivalent materials in order to produce a p-type or an n-type material. Similarly, in a bulk material, if you have certain ingredients of nanoparticles, then also the physical properties, they change dramatically with the added nano ingredients. In this video, we have started our discussion by understanding the roots of the word nano. We have said nano is a word in Greek which means dwarf or small or very, very small. Mathematically, a nano means billionth part. In physics, it means a billionth part of a unit. We have seen how nanometer can be expressed. We have discussed a couple of examples, and we have said that nano world is a borderland for quantum world and the macro world. We have seen on a range of lengths of 0.1 nanometers to 1 centimeter various entities that are known to us. We have seen some examples of size from molecular to macro. We have seen the significance of the nanoscale. We have said that nanomaterials have a relatively larger surface area when compared to the same mass of material produced in a larger form. The second reason we have seen is quantum effects can begin to dominate the behavior of matter at nanoscale, affecting the optical, electrical and magnetic properties. Thirdly, we have seen the physical properties of materials are generally characterized by critical length. We have seen an example to understand this, that is the mean free path of an electron in electrical conductivity. Lastly, we have seen that the bulk properties of materials often change dramatically with nano ingredients. We have explained this using the extrinsic semiconductors. Similarly, in the case of nanomaterials also, when the nano ingredients are added to a bulk material, properties of the bulk materials are also dramatically going to change. Thank you.